As we mentioned before, the rate constant K is not a constant. It does vary with temperature. And in general, although this isn't always true, in general it goes up as temperature goes up. Reactions are faster at higher temperatures. So there's a way of explaining this, which is the Arrhenius equation. And the Arrhenius equation is based on this idea that we start off, if we look at energy and reaction progress, that's called the reaction coordinate, sometimes just labeled as RC, that we can draw a graph like this, where we've got reactants, products, and a transition state between them. And this distance, this difference here in energy between our reactants and our transition state is called the activation energy. And although it looks like it's a peak, it's really a saddle point, because although along the reaction coordinate this is the highest energy, we could of course arrange the atoms in other ways that is not along the reaction coordinate. So for instance, if we're talking about an SN2 reaction, if we flex the other bonds in ways that lead to higher energy, that would be even higher than this. So the way to think of a transition state is it's like a mountain pass. So along the direction of the road, a mountain pass is the high point. But of course, on either side of the road, there are mountains that are higher still, and those would be orthogonal to the drawing that I put on the screen. In other words, they'd be behind the screen or below or in front of the screen. Okay, and of course, this is the one I've done is one that is having products lower, but we could just as well draw an RC diagram for a reaction that looks like that, right? We could have products having higher energy than reactants. So that'd be perfectly fine. Many reactions are like that. Okay, so the Arrhenius equation is a way of modeling how rate constants depend on temperature, and it's based on that activation energy. So this activation energy determines how sensitive the rate constant is to changes in temperature. The A constant can be thought of at this stage as something that just basically based on things that are not energy dependent. So for instance, orientation. So molecules not only have to have enough energy to react, but they have to be oriented correctly. So the question is, how general is this equation? Well, it turns out if you look at many reactions, they follow the Arrhenius equation quite nicely. But also if you look at fireflies. But also if you look at fireflies, which we don't have here in San Luis Obispo, but I'm sure you've seen them in movies, if you look at the number of flashes per minute, we can actually model that rate using the Arrhenius equation. It's temperature dependent. Or even if you looked at something like the flow of liquids, which of course is dependent on the inverse of the viscosity, it's going to be something we can model with the Arrhenius equation. So this is actually quite general, because all things, whether they're chemical reactions in fireflies, are based on the idea of rearranging bonds in molecules. Let's see if we can pick up some trends by looking at this data. First of all, we notice something about complexity of reactants. If complexity of the reactions goes up, what does that do? Well, here we have a simple atom attacking. Here we have two molecules attacking each other. And here we have two radicals attacking each other. And notice the one with, by far, the biggest pre-exponential is the one where it's just a simple atom attacking. That actually makes sense, because if A is a measure of how hard it is for the molecules to get oriented in the right position to react, with the more difficult it is, A being smaller, we can see over here, oxygen atom, of course, is a sphere, so we don't have to worry about orientation at all. We only have to worry about orientation with regards to how this molecule is oriented. So if we think about this, we might have an oxygen atom as a sphere, and then we've got the nitrogen atom as a sort of an oblong, and we're looking at the two different modes of attack. Of course, only one of those is going to be oriented correctly, but at least we don't have to worry about the orientation of the oxygen itself. So this is actually backwards. The bigger the complexity, the harder it is to get oriented correctly, and so A goes down. And that's what we see with these. These have a lower A. We also find out that if we have to break a lot of bonds to start the reaction, then that's going to mean the activation energy is going to go up. So if we look over here, we have to break this bond to do the reaction. We have to break this bond to do this reaction. Over here, we don't have to break any bonds. We've got two methyl radicals, and those hydrogens stay bonded to the initial carbons. All we have to do is form a bond. And so here, the activation energy is essentially 0. Let's look at one more case. Let's do a solution phase reaction. And this will also be second order. So let's have ethyl bromide reacting with hydroxide radical or hydroxide ion in an SN2 reaction to give ethyl alcohol plus bromide. Now in this case, A is equal to around 4.3 times 10 to the 11th. And that's in the same units as the rest of the table. And activation energy is equal to around 89.5 kilojoules per mole. So the activation energy, it's not really different from the gas phase reactions. But this, notice, is on the very high side, even though these molecules are quite complex compared to this. They're molecules, they're not atoms. So why is the A factor so high? Well, in a gas phase reaction, the molecules bang into each other and then they bounce apart. If they're not oriented correctly, there's no reaction. In a solution phase reaction, the molecules are surrounded by sort of a solvent cage, right? There's all these solvent molecules. And so the A and B molecules can bang into each other many times before they separate. So what we say is there's one encounter that's composed of many, many collisions. So even if they're not oriented right the first time, on the next bounce or the third bounce or the fourth bounce or whatever, they might be. And so A constants tend to be fairly high for solution phase reactions. So let's just put that here, that if we're in solution phase, we're going to have a much higher A constant, much higher pre-exponential factor than we would for a gas phase reaction.